Great. All right, guys, welcome back after a short break, or maybe not so short. I hope you had some vacation or a little bit relaxed from your studies, but now you have to still bear with me for a couple of lectures. So you will have to listen to me probably, maybe if I'm lucky, this lecture, maybe half another one, and then we'll have two invited speakers. So you will probably have 1 or 1.5 lecture of on natural language processing and mining natural language, and then on privacy preserving data mining. So this, but this will be more of a probably maybe hopefully easier topics. Although I also believe these were not that difficult up to now as well, because this is a basic data mining course. So today we will wrap up, or try to wrap up, things that we learned and use the tricks and definitions and tools and whatnot we learned in the last 9 lectures to sort of for doing something more useful. And you will see that in some cases we can do very well, in other cases it's it's so-so, but that's how this data mining field is about. It can be a bit dirty, and then you have to hack and do some cut corners. But in the end, I hope you will learn something useful, and in your projects you can see that you can extract something interesting from the data sets you have. So before jumping directly into today's topic, I want to simply remind you what we had a few lectures back. So remember, we looked at the clustering problem in general, not from graph perspective, but said if you have a bunch of points, how to cluster them. And then we went through the main algorithm that you will find in the area. And then we looked at the label propagation techniques on graphs, when you could think of it as a semi-supervised learning approach, where you have some of the nodes labeled and majority of the nodes not labeled, and then you want to infer what these labels could be. And then we had sort of 2 classes of the algorithm. One is that the ones that are labeled never change their label, so never change their identity, or whoever the expert labeled or how you extracted it, it never changes the label. And the other type was that it can change, maybe diffuse, sort of it starts with one label and then could maybe get another label, and that could also be the case in real life when the data can be noisy, dirty, and not correctly labeled. But now I want to invite you to think just at the graph structure, and we don't have any labels, and we still want to extract something, clusters, and up to now we already even had several algorithms that extracted clusters, but we never looked formal at it. What does it mean, there is a community or a cluster in a graph? So how would you define, without looking at labels, we don't have any ground truth, we just have a graph. Let's say a social graph of your class. Right? If I drew, you have like 30 people, I would draw your say friendship on Facebook links, and then I believe there would be some communities. Now, first of all, how would I identify these communities? How would I say that this community is valid and this is not? Like this set of nodes form a community and this set of nodes do not form a community. What would be your suggestion on how to select a set of nodes from the graph that you would claim this is a very good community?
Lots of interconnection within the community, but not a lot of connection out of it.
Right. So this is what your friend said, is basically describe the generic rule that what we want, when looking at the topology, is that the connectivity within the community that you selected, that you propose as an output, should have a more internal edges than external edges. And then there are many, tips and tricks how to sort of measure it, and we'll go it today. So, in a sense, this community structure captures, this phenomena that in real life the networks emerge not randomly, as we already discussed, but with some kind of phenomena that drives them into the non-random connectivity, and therefore non-random connectivity creates some islands somewhere and some gaps somewhere else, and this then can be captured by this some kind of community measures. And in a sense, set of nodes with more or better or stronger connections, can be outputted as a specific community for our graph. So let's say this graph, it's quite easy. How many communities we have here? It's probably, everyone sees 3, right? But now if I put an edge here, is it still 3 or now 2? I mean, okay, again, this is not there is no right or wrong answer, but if this was quite easy and any, in a sense, evaluation measure would give you 3 communities, this is not that easy, and maybe defining certain evaluation measure could give you still the 3 ones, or maybe it would, one of the sort of measures, somebody could argue that this is a 1 community. And that's what we're going to look at in today's lecture, is how to say whether this was correct, or is it a 3 clusters or 2 clusters. Okay, so there is not really, like, you will not find somewhere a clear definition of what is a community in a graph, so we have to a little bit play, we collect from many different sources, papers, what researchers and people thought what is a good community, but this will be like a collection of sort of state-of-the-art research on that, and classified into the main blocks and how communities are defined. So let's see. And of course, I just want to tell you that the way we look at the community, let's say even here, would depend on what kind of problem you're solving. And maybe for one problem, this would need to be 3 communities, another problem, this would be 2 communities. So that's a domain specific as well. So, also, let's remind ourselves, like usual, that we talk about sparse graphs here. Of course, you can apply the same measures for the dense graphs, but then it becomes maybe a bit less intuitive, and then we might need to go to the weighted graphs. But for a moment, just think about sparse graphs. And we will later look at the mostly also bidirectional graphs and very little on the directed graphs, because directed graphs complicate things very quickly. Also, I just wanted to remind you that extracting communities is not easy. It's NP hard problems. So whatever even if you know the right measure, how to measure good community, if I will give you a specific sort of measure saying take a Facebook graph and extract the communities with the best edge cut, you might not be able to do so because you cannot exhaustively check every single subset and measure its quality. So you need to use some heuristics, some hacks in order to do that, and you might not ever be sure that you found the best global optima. But that's usually the case what we have to live in the real world. So you have to do the best and hope that whatever you proposed is good enough, and your local optima is close to the global optima. Okay, so again, if you take a Facebook graph, how would you define a good community? So say if you are in a Facebook, what would be or let's say in your Facebook group, what would be a good community? What do you think? Like take your own Facebook profile, you have probably some hundreds of friends. In what type of community would you put yourself? Because definitely, I mean, you are in a Facebook graph. I assume most of you are on Facebook. So we have a Facebook graph. And this Facebook graph is not random, so we can have some kind of a structure there. So now tell me if you would probably belong to some community, and what this community be about. What do you think?
International students at KTH?
Sorry?
International students at KTH?
Yeah, so that is one of the probably way to look at the partitioning. So if you partition in certain way Facebook graph, you could figure out that this community is like your international students. Or maybe this would be people who like football. Or maybe these who live in Stockholm. So my point being is that there are many valid ways to cut the graph into the partitions. So there is not one unique way saying that this is a graph, this is how I cut, and there is no other way to cut it. And it's true that maybe certain graphs, like the one I drew in the beginning, has more or less the only way to cut it. I mean, the first instance where there are 3 clusters. But like for the second one, maybe it will be already a bit ambiguous. And then communities can also become overlapping. We will not cover in this course overlapping communities. But so what I want to say that there is, you cannot, while doing data mining problems, you cannot just say you take a graph, you do some kind of clustering that gives you some communities, and then you believe that this reflects the domain you are looking for. Because if you were looking for football or sports-related clusters, but you extracted international student cluster, it's wrong, right? So that you have to be careful. So you have to remember that every graph has a, I can't say every graph, but many graphs are built not by a single phenomena, but by multiple phenomena. And like in real life, your Facebook links happen because you like football maybe, or some sports, or because you have certain hobby, or because you live in a certain place, or because you study in certain group, and many other ways. So there are many driving sort of forces that create the graph. So you cannot just say that it will all be, say, embedded in geography. I mean, you could say that maybe geography has the biggest component, and the partitioning geography would have quite good clusters, but that would not maybe take into account long-range collaborations, because collaborator in Europe and in the US by geography will be already in different communities, while they maybe talk by Skype every day and are very good friends. So there are many ways to look at it. So okay, so now coming back to how we're going to measure, and this is what your colleague just said, that a community corresponds to a group of nodes with more intra-cluster edges than inter-cluster edges. Basically, more inside, less outside. So our plan of action will be the following. So first we're going to define a quality measure and how we are going to evaluate whether the community is good or bad. And then we're going to find an algorithm that extracts the best community given that measure that we just invented. And we will go now through these measures. So there are a lot of measures, but most of them fall into these sort of 4 classes. So one measure is sort of based only on internal connectivity. So when you start counting the variance of number of edges within community. Another one is based only on external connectivity. So you don't care about how many edges are within community, but you care how many go out of your community. So usually you try to maximize the first one. You want to be the inside edges as dense as possible, and you want to minimize the second one, external ones. You want to make as small cut as possible, because that defines a good community. And there are also the sort of set of measures where take both internal and external with some ratios. And then the fourth one takes into account sort of the whole picture, the whole graph, when it compares, in effect, how current graph is different from a null model, like a random graph. So whether the community, in very sort of in layman terms, would be whether if you say take this node as a community, I count number of edges within that community, and I compare if this number of edges are similar to the one that would happen by accident in a random fashion given the same degree sequence. And if it is similar number of edges, it means maybe it's a random graph. It's also the random connectivity. It's not really a community. But if it has much more denser connectivity, then I claim that this is a quite good community, and that's what we'll call modularity. So we'll look at it a bit later. So, okay, so in order to go now through this set of evaluation measures, we have to establish the notions, and most of them you already seen, but I will try in the next couple of slides color everything in this sort of 4 colors. So the community I'm going to evaluate will be with the green nodes, and this would be like S set of nodes in the cluster that I'm going to evaluate how good it is. The blue or the internal edges would be red, so I will count MS will be the number of edges in this community, or in this set of nodes that I say this is a cluster. Then the blue edges will be edges going out of the community to the outside graph. So this will be like CS, or it corresponds to a cut. As you would think, if this is my community, then I cut edges, the blue one edges here that crosses to the rest of the graph. And then, you know, the D would be the degree of the node, and the N, big N, N without an S is overall number of nodes, and M is the overall number of edges in the graph. And we are now going to try to find Fs, which would be a measure in how to measure the quality of a specific cluster. So the first most naive way that represents the first class internal connectivity is just if Fs is a measure of a number of edges inside the cluster. Just Fs is equal ms. So that's you could say my cluster. I tell you this cluster, and in the goodness measure is 1, 2, 3, 4, 5, 6, 7, 8. Goodness measure is 8. Now, maybe it's not the best measure. How would you improve it? That it'd be a bit more informative.
Divide by the number of nodes.
Very good. So that could be, you know, you normalize by the number of nodes. Or I think the next slide is, it's not, we will come to this in the one after. One other way is to normalize somehow. One is number of nodes or number of edges. So if you say that there are 8 edges in the cluster, it doesn't tell me much, but if I tell you that out of that many possible edges, that suddenly becomes more clear, right? Because remember, if ns is the number of nodes in the cluster, then ns times ns minus 1 divided by 2 will be all possible edges that can happen within these 5 nodes, and then this will be the ratio. Then if the ratio is very large, then already can, and that will be from 0 to 1, right? So then instead of 8, I could now see, it's maybe 75%. That's maybe good. Or maybe it is only 2%. That's maybe not so good. And that could give me, so that's called internal density. Now, what your friend just mentioned, you could also divide by number of nodes, and that would make an average degree. Basically, you just divide, in a sense, you see how many these edges fall for every node, and then you see what's the average degree. That also could be a good measure of the internal goodness of the cluster. There are more fancy ways. For example, you can measure fraction over median degree. So in a sense, you first find out what is the median degree of the graph. So maybe median degree is, in Facebook graph, I don't know, it's maybe 355 nodes, 55 neighbors. And then you see, given the specific cluster, what's the fraction of the nodes in that cluster that have a larger degree than the median degree in the graph. And if you have a cluster with a much larger degree than the median degree in the graph, maybe you have a good cluster. Then another one, which is also we still talk about internal connectivity measure. So it's all about this red edges. We don't touch the blue edges just yet. we talk about triangle participation ratio, or in a sense, in the normal language terms, how many triangles there are in this cluster, normalized by all number of nodes. So again, if you have many triangles, that means maybe your graph is quite well and densely connected on your community. And if you have a high ratio, you might have a good quality community. Now we can go to the external connectivities. Up to now we were, all of the designed, the goodness functions were involving mainly the red edges. Now we need blue edges. Do you have some suggestions? What would be? And we already actually covered one in the previous classes when we were trying to play bad guys and to cut the internet. Remember when we were discussing expansion. So expansion is one of the external connectivity measures, and you can sort of measure with how many cuts can you isolate how many nodes. Yeah, so this will be the number of edges that are leaving the cluster normalized by the number of nodes that you isolate. So that's expansion measure. That's very often used measure. Another one, it's called very similar to that. It's called cut ratio, where again you measure how many edges leave the cluster versus how many possible edges could have been here. And possible edges could have been here will be basically that number of nodes multiplied by that number of nodes, right? So the ns times n minus ns, right? So that would be the cut ratio. So these are the very often used measures in defining the quality of the cluster. Now we go for external and internal connectivity. So now we take into account both of them. Any ideas? Yes?
Yeah, the ratio between the edges inside and the cut edges.
Yeah, so that's exactly what we're going to do. It's just sort of a small variant of that. It would call conductance, and we would take the leaving edges versus not exactly the inside edges, but in a sense the sum of the degrees of the green nodes. That would mean you sum up red edges twice, and once the blue edges, because they have only one side in our cluster. So in a sense, you go through every node, you sum up their degrees, and you put it in the denominator, and in the numerator you put the cut, and that would give you a conductance. So in a sense, then you measure both at the same time. You have both the blue and the red edges. There is also, I mean, this can be a bit tricky because in that case, very sort of good conductance measure could be, for example, a single node that hangs out. So if there is a graph and there is a node, then you always will try to say, this is my very good cluster because there is only one edge leaving, and there are basically 1 over 1 because there are no edges inside, so it's a perfect cluster. So in order to avoid such a small measures, you would need to, it's called normalized cut, where you take not only that side of the cluster, but also plus the conductance of the overall cluster, which basically sort of you will look from that perspective and normalize by that number of edges. So that would give you sort of more balanced cuts, which is a normalized cut. Then there is another term which is called average out degree fraction. So for example, again, this is simply to measure, you first measure at every node what's the fraction of nodes that leave the cluster. So say if we now play our cluster Stockholm, and if we look at our Facebook friends and see how many friends are in Stockholm and how many friends are out of Stockholm, and maybe I have I don't know, out of my 500 friends 200 are in Stockholm, so it is 2 over 5, 40%. And maybe you have out of 1,000 friends, 50% in Stockholm, so it is 40%, 50%. We add all our percentages, make an average, and that will be the our average out degree fraction. So you see, what's the average degree, average fraction that leaves our cluster? And of course, the less it leaves, the better it is, because if you have a very little edges leaving the cluster, you have a very good quality cluster. And the last one is this, the fourth category, based on the overall graph. Here we actually, as I said before, try to measure how this cluster would have looked if we just did things randomly. And to calculate it, you will see in many papers, they always, well, not always, but very often you define a matrix which is called modularity matrix. And this modularity matrix has sort of two components. So it's actually, it's an adjacency matrix minus, so you can see that another matrix where at every cell you would put a value. So let's put it that way. So we have a adjacency matrix A. So our modularity matrix B would be adjacency matrix A, and we know it's basically ones where we have a link from I to J, minus now another matrix, and that would be a dense matrix, where you calculate for every I and J the probability that the edge would appear among them at random given the degrees of I and J. So if I has a degree di and J has degree dj, the probability that we will form an edge there at random, like with a null model, would be di times dj divided by the whole number of basically of the sum of all degrees, which is 2m. And then you do it for every cell. And then when you basically this you have what you observe in a graph, and this what you have what you expect to happen at random. You subtract, and then you take into account only now some kind of cluster. So let's say I say this is the cluster from 1 to to 20. Yeah. So then I would take this part of the matrix, will sum up all ones, maybe, and find there whatever 7 ones, 7 edges in that cluster. And that means that there are edges going from somewhere in the cluster to somewhere else in the cluster. And we'll subtract all the sort of the random chance contributions that the number of sort of what's the expected number of edges should have appeared in this cluster pure at random. And if it is around 0, that means it's a random cluster. And if it is much larger, then it's not a random cluster. And basically you usually do it again with the linear algebra help. So if you now define this B in this way, by this, so in a sense what you have is now is this B is a matrix where it's already subtracted from the observed and the random, and what you need is a vector S that says which nodes I now test as a set. Let's say I test this, the third node, the fifth, the sixth node, the seventh, and the 10th node I will put in my set, and I want to set this up to be evaluated. So I make a vector S where I put ones into the places where I want to keep the members of that specific set here, and in that specific case would be S would be only 1, 1, 1, 1, 1, the first 20, and then the rest would be 0. And then if you do such a vector where you have ones in a specific places where you want to test the want to put the members of the set, multiply by that B, and then multiply again by the same vector just transposed, you in effect filter a specific region I mean, if it is all ones here, it would be exactly that region summed up here, or if there are specific places, not continuous like ones, then it will take a specific, cells and sum up, bringing you the actual sum of the or the expectation of observed minus the random edges in the graph. And then if that gives you something around 0, that means there is not much of modularity. I mean, that means your cluster is not very pronounced, or maybe it's not pronounced at all. And if it is large, you can claim that this is a very good cluster. And that's also very often used in evaluating how good the sort of partitioning is. And maybe in many papers that you read, people said, oh, and the modularity of that graph, of that partition is blah, blah, blah. So usually they do it by these calculations. And then you can normalize it by the number of edges. So okay, so now and this is by no means the exhaustive list of all the possible measures. I'm just gave a sort of a selected few that I saw in some papers, but you might find the other ones as well, and maybe even invent your own if you like. But in any case, I think, again, I don't want to claim that maybe you can make some fancy new categories, but there are these 4 main categories: internal, external, and the global modularity-based evaluation measures. And then you basically have to choose one of them for your problem. So now, which one to choose? How would you now? And again, this is a question with not a right answer. I just want you to think a bit and speak up. What would be your favorite measure? How would you? Just I mean, again, there's no right or wrong answer. I just want to see your your ideas. Yes.
The second one.
the external, yeah. Why?
Because the first one is very naive, the last one is very costly, and the third one, the thing that we have to check the degree of the rest of the network is costly as well.
Yeah. Okay. So very nice. So you already start thinking what is the cost, and whether it's easy to evaluate one or not, and that's very good. But what I was after was maybe a bit different. What I was after is the following: that the fact that we have, for example, now forget about the cost. So say you take some kind of internal edges measure, say the average degree measure versus say expansion measure. And now you have a problem. And the problem is, again, let's come back to the same what we discussed. Attacker wants to cut the internet, right? So he wants to see where are the best sort of links to cut. So want to identify a cluster that can isolate most effectively. So the attacker might want to go for expansion rather than internal connectivity. Because internal connectivity, while could give not a bad cluster, it doesn't really say whether the outgoing edges would be large or not. So whether you need to work a lot with the scissors or not. So what I'm after is that the way you might need to choose your measure will depend on your domain. And in certain cases, maybe it doesn't really matter because the graph is so simple, like the one that we saw before, probably every of the measure would give the same output. Because it's super, like there is no degrees of freedom. There are 3 clusters, and you take internal or conductance or the modularity or whatnot, all of them will say these 3 are the best clusters. But if the graph is sort of very fuzzy, like a social graph, it's because it's made by multiple phenomena. And maybe, again, I'm not saying that it's true, but I'm just saying that, for example, maybe the way to find your people who work in international students would be triangle participation ratio, while you know, the way to find some kind of say who belongs to which community in Stockholm municipality would be maybe expansion, because the phenomena behind is different. So that's why there is no really a right or wrong answer that this is good, this is bad. But for your problem, for your domain, there might be only few or maybe only one that is the most sort of useful, and the rest might be actually wrong. And again, in many graphs, you are quite safe because all of them will give the same output. But if you have a very sort of tricky graph, this might make a difference. And there was a paper, I'll put it online, where they actually did exactly that. They took a lot of communities. How many? There were 230 communities, or 230 graphs with the tagged communities. So they went really like the same what you did, just all together in your project. So they had these 230 data sets. They also had ground truth. So somebody actually tagged that these are the international students, or these are the footballers, these are, I don't know, whatever the graphs they had. And then they tried to see which of the measures the best capture this ground truth. And they said that on average, if you want now to have a sort of one-size-fits-all answer, is that conductance and threat, or this triangle participation ratio, give the best performance. So if you want not to bother fine-tuning, just go for this one of these two. Because by this like exhaustive search of a large number of graphs, these give quite good output. But then, of course, if you will want to fine-tune, and maybe you will see that in certain specific cases, these were not the best. For I'm sure out of these 230 ground truth communities, some of them were much better identified by other measures, because maybe they had different problem, different phenomena constructed this graph. Therefore, you had to go for different sort of evaluation measure. And that's one thing, is to understand how this data mining problem is related to the evaluation measure you choose. And then once you have, and that's difficult, that's not what I'm going to teach you. This is sort of an art. This is, you have to do it on yourself, and maybe even be lucky that your problem is either easy enough that many of those or all of those capture, or you really think what is the phenomena behind, how it's similar with what we discussed with this malicious attacker, what would be the mapping between the problem you're solving to the community definition in your graph. But then later, that's not all. That's only how you will evaluate. Now we have to find the algorithm that would extract that community. Because if you say decided that your problem requires edge cut or conductance, but your algorithm is solving for internal density, it will give you some not bad communities, but will be not the best communities. So you also need to later adjust the algorithm appropriately. So in the end, it depends on the problem what you are solving. And again, I want to just remark that since this is a quite very recent field, so there are no well-established namings for every of this measure. And sometimes I saw that often conductance and normalized cut is used interchangeably. So again, often when you look at my slides and in some random paper, it could be that there is a mismatch with naming. So it's always better to look at the actual formula, what they measure, and the naming is sort of is the secondary. So I will, don't worry, in the exam there will not be like give me a conductance formula. It's more, if I will ask something about conductance, I will give you the formula, and then you will have to argue something about it. So now all this now boils to the fact that this was the difficult part. Both easy to, in a sense, to just chat, but I cannot give you exact answer which one to use. That will be now depend on your problem and on your graph. But once you decided that I'm going to extract communities that are, that will be evaluated by a specific measure, then I have to define an algorithm that is going to give me the best output of that specific measure we were sort of came upon. And this will now bring me to the next part of the lecture, which is spectral clustering. So spectral clustering, I'll give you now examples from each of the class of this internal, external, and modularity, how using graph spectra to extract communities that cater best for one of these evaluation measures. So in order to do spectral clustering, you have to, by almost definition, you have to now move again to linear algebra, which we always were partially one leg there anyway. And again, I want to remind you that every graph is a matrix, every matrix is a graph. So think about that way. And as a matter of fact, any data set you can convert to a graph. Just in some cases it would be a dense graph, but it still would be a graph. So what you need to do, you need to end up with a what we would call similarity affinity matrix. And it does not need to be a adjacency matrix, because adjacency matrix implies there is only zeros or ones, and usually implies it's sparse. Of course, it's nice when it's sparse, and that's a graph. But if you have something else there, so say you have a bunch of data points, and if you can measure the similarity or affinity between any 2 points, you can make a matrix, right? You can say this point with this point is similar 2.3, and this one is similar 0. And that one is something else, and then you can fill in this matrix, and that will give you affinity matrix. It's not exactly like a straightforward, you can say it's a graph, but every matrix can be thought of a graph, and if it is some kind of non-zeros ones, it will be a weighted graph. And we can do a very perfect sort of clustering techniques on weighted graphs as well. What you have to take care of in order for those spectral clustering to work and our linear algebra to make sense, all the values should be non-negative. So that's a property of otherwise our spectral clustering would not work. So whatever you do, if you now take your bunch of data points and you invent some kind of similarity affinity measure, you have to make sure first that the measures always should output a positive number. And what's another thing which is important, and I saw some even with my PhD students, they sometimes get confused. You might get sometimes confused that you might say that the more similar you are, the closer to 0 you are. And the more dissimilar, the closer to, say, 1 or to the larger numbers you are. But that's not the case what spectral will be solving. Spectral will be solving the opposite. The affinity matrix should be the following. The closer to 0 you are, the more dissimilar you are. And the closer to it doesn't need to be 1, it could be just any larger number. The more larger you are, the more similar you are. So if you sort of comply to this, and one more, there are many complications here, and it has to be symmetric. Because it's not symmetric, then again it makes much more difficult linear algebra and spectral clustering. So what you have to just do, you have to do a symmetric affinity matrix out of your data. And if you have a graph, it's already there. If you have, it's a sort of an instance of that is an adjacency matrix, which is zeros and ones by definition. But if you have something more complex, you might have even a dense matrix where you measured a distance between or some kind of similarity between any 2 points. It should give you a positive value, and the larger the value should indicate the better similarity, and the smaller the value, the smaller similarity. And the idea is that this matrix, in order all our spectra to make sense, should be positive semi-definite. And I'm not sure if you took a linear algebra course, but it's not a. So okay, this just to explain, positive semi-definite matrix is such a matrix that act on a vector in a specific manner. So vector is nothing else as some kind of a vector in some, you know, large dimensional space. And if you multiply this vector by A, it's as if you hit the vector with A, right? And then you can see what happened with the angle when you hit with A. And how can you know what happened with the angle? Basically, you take initial x, you take the x that you hit, and measure the angle or the dot product. So this is what you do. You take x times a, which is, you hit the x with a, times x, we do the dot product. And if it is more than 0, it means the angle, it was less than 90 degrees. Okay? And if it's less than 90 degrees, it's positive definite. If it is, I think, strictly less than 90 degrees, and semi-definite, it can still be 90 degrees. And if this is the case, then A will have n non-negative eigenvalues. And that's what we want to do, because that's what we're going to look at the spectra, and this is the spectra of A. But if you follow what I asked, if you don't do your similarity measures, negatives, and you know it's symmetric and follow these rules, then you will have a positive semi-definite matrix A, which would now help us to do spectral clustering. And again, I want to emphasize that sometimes you have, by definition, because you have a graph. So this is if you don't have a graph, you want to construct, in a sense, a graph or this affinity matrix. But sometimes you already have initially graph. You just get adjacency matrix, and you are sure this is the case, and you can now go on to the next slides, which we'll look at after the break. So let's have a 10-minute break, and I will continue with spectra.